table. And then another neighbor of node C is E, right? So we look at node E. So can we accept the new information? Can we use the new information to update our table? If we do not use the information, we can say that shortest path from node A to node E, from the starting point to node E is infinity, right? We cannot go from node A to node E. And here, if we have this new information that we can go from node A to node E via node C, definitely we should accept this new information, right? We should use it to update our table. And the length is 2, right? Because it is 1 plus 1. And the predecessor of node E in this way is C, right? So we should use this information to update our table, which is like this, right? So here, after we traversing all the neighbors of node C, we have used out all the information that node C gives us, right? So here we should mark node C as visited, right? Use the check symbol, and then we should look at another node. The next node we should look at is B, because it had among all the visited nodes, it has the shortest distance, right? Which is 2. Because if you notice, if you see that for node E the distance is also 2, but we should do it alphabetically, right? So we use node B in this case. For node B, let's look at node B's new information, and it has a neighbor E, right? So let's look at node E. For node E, if we do not use this new information, we can see that we can go from node A to node E via node C, right? The length is 2. And if we use this new information, we can see that we can go from node A to node E via node B. And for node B, we should also via node C, right? So here we should choose A, C, B, E, and the length is 4, right? So because it is larger than our current distance, right? So we do not accept this new information, so we do not need to update node A, right? And then, as we say, for node B, it then does not have another neighbor, right? So we finished the node B, right? We have used out all the information for node B, so we mark it as checked, right? As finished. And then the next node with the shortest length is E, node E, right? We want to use it to update our table. So the first neighbor of node E is node D, right? So let's look at node D. For node D, currently, if we do not use this new information, the shortest distance from node A to node D is 6, right? And we should via node C, right? And if we use this new information, we can see that we can go from node A to node D via node E. And for node E, we should go from node A to node E via node C. So here, we choose this path, right? And the length is 1 plus 1 plus 3, which is 5, right? So which is less than 6. So we should accept the new information, and we should update our table, and the predecessor becomes E in this case, right? So here we got the data. And let's look at the next new information, which is from node E to node I. Let's look at node I, right? So currently, if we do not use this new information, we can say that the shortest distance from node A to node I is infinity, right? So definitely we should use this new information. So we should go from node A to node I via node E. And for node E, we can see that we should go from node A to node E via node C, right? So we should use this path, and the length is 8, right? So we update I using 8E, right? And we have finished the node E, right? So we mark it as finished and checked. as visited, right? So then the next node we should look at is node D, right? So similarly, we should look at its first neighbor node E, and using this new information, can we update our table? The answer is no, right? Because the new information did not give us a new lines or a smaller pies, right? So we should look at another neighbor of node D, which is node I. And for node I, we can see that. And currently, if we do not use this new information, the shortest distance from node A to node I is 8, right? So if we use this new information, we can see that we can go from node A to node F via node D. And for node D, we should go from node A to node D via node E, which is this. And for node E, we should go from node A to node E via node C, which is this, right? So we form a new pies, which is from A to C, from C to E, from E to D, and from D to I, which is of length 7, right? 2 plus 3 plus 1 plus 1 is 7, and it's less than 8. So we should use this new information to update our table, which is like this. The predecessor becomes D, right? So we have used out all the information that node D gives us, so we mark it as visited, and then we should go on to visit node I. So this is wrong. We should use I here. And for node I, do we have new information? No, it does not have any new neighbors. So we finished. Then based on the table we have updated, we have used out all the information that all the nodes can give us. So we can see that the shortest path from node A to node I here must be via D, right? So here here we should go from node A to node I via node D, from A to I via node D, and for node D we should go from node A to node D via node E. So here, so we just go backward, which is like this, right? And for node E, we should go from node H to node E via node C. So here we backward like this, right? And for node C, we can see that we can go from node A to node C, and the length is 1, right? So here, so basically we can have a shortest path, which is like this: A, C, E, D, I, and the length, the distance is 1 plus 1 plus 3 plus 2, which is 7, right? So basically this is the idea of how to use a Dijkstra algorithm to solve the shortest path problem. And that's all. Thank you.